What's going on? Today, well, I'm going to be one-tapping concurrency. What does that mean? It means I'm going to be reading this chapter on operating systems, or this collection of chapter on operating systems for probably the next 6 hours. I just got out of OS lecture, actually, and I was thinking the whole time, dang, I should probably really work on this project. I should probably work on my processor design project. Well, I should probably work on Gleam. I should probably work on some other open source project. Do I really want to spend the next 6 hours just reading? And then I was like, walking back. Dang, I really don't want to do this. I don't really want to sit in a chair for the next 6 hours doing approximately nothing. But now I'm sitting here, and I want to finish this book. And that implies having read the book at some point in the future. And so, why not do it right now? Enough said. Today we have, appears to be 10 chapters, though the dialogue and summary are short and useless. Part 2 concurrency. That's just like some entertainment. And so, let's just get a kind of feel for the page counts here. So 16, that's probably about the average. 12 is definitely short. 22 is the longest yet. 16 average, I'd say. 19 among the longest. 20 among the longest. Concurrency problems, event-based concurrency, 12. So, yeah. Along with this, I'd like to do these sorts of exercises, these p-thread exercises. And so I'll go ahead and make a, let's see where I was working on earlier. Let's go ahead and make a temp. Make their concurrency, cdcon, clear, make this bigger. And we're just going to end them here. And also we'll make it smaller and then make it small in this axis. Scoomy. And like that. And then we'll just have GCC. Okay. So yeah. Just do a quick check here. Sound viz looks good. That looks good. Let's get into it. Concurrency, an introduction. Thus far, we have seen the development of the basic abstractions that the OS performs. We have seen how to take a single physical CPU and turn it into multiple virtual CPUs, thus enabling the illusion of multiple programs running at the same time. We've also seen, how to create the illusion of a large private virtual memory for each process. This abstraction of the address space enables each program to behave as if it has its own memory when the OS is indeed secretly multiplexing address spaces across physical memory. This is also where Trumanov loves saying multiplexing. I think I've heard the word multiplexing more in his lectures than in any book or conversation all time. Fun fact. Shout out Dr. P. This chapter, we're going to talk about a abstraction for a single running process, that of a thread. Instead of our classic view of a single point of execution within a program, i.e. a single PC where instructions are being fetched from and executed, a multi-threaded program has more than one point of execution, multiple PCs, each of which is being fetched and executed from. Perhaps another way to think of this is that each thread is very much like a separate process, except for one difference. They share the same address space and thus can access the same data. The state of a single thread is thus very similar to that of a process. It has a program counter that tracks where the program is fetching instructions from. Each thread has its own private set of registers that it uses for computation. Thus, if there are two threads that are running on a single processor, when switching from one, T1, to the running to running the other, T2, a context switch must take place. The context switch between threads is quite similar to the context switch between processes, as the register state of T1 must be saved and the register state of T2 restored for running T2. Okay, so the must, he's duplicating the must. As the register state of T1 must be saved and the register state of T2 restored before running T2. With processes, we saved state to a process control block. Now we need one or more thread control blocks to store the state of each thread of a process. There's one major difference though. In the context switch we perform between threads as compared to processes, the address space remains the same, i.e. there is no need to switch which page table we are using. So the classic question, what is the difference in a process and a thread? From here, I can say that, what can I say here? Well, I can say that threads do not have a page table because they share page tables with the parent thread that spawned them. So one thing in similar is that they both have a program counter and a working register set. I think that's all I have currently. One other major difference between threads and processes concerns the stack. In our simple model of the address space of a classic process, which we can now call a single thread process, there is a single stack usually residing at the bottom of the address space. However, in a multi-threaded process, each thread runs independently and of course may call into various routines to do whatever work it is doing. Instead of a single stack in that address space, there will be one per thread. Let's say we have a multi-threaded process that has 2 threads in it. The resulting address space looks different. So you have a stack for each thread. You share a heap and program code. Any stack allocated variables, parameters, return values, and other things that we put on the stack will. So freak the headphones. Okay. Return values and other things that we put on the stack will be placed in what is sometimes called thread local storage, i.e. the stack of the relevant thread. You might also notice how this ruins our beautiful address space layout. Before, the stack and heap could grow independently and the trouble only arose when you ran out of room in the address space. Here we no longer have such a nice situation. Fortunately, this is usually as okay as stacks do not generally have to be very large, unless you're making heavy use of non-tail optimized recursion. Facciamo threads. Dispose of threads. Before getting into the details of threads and some of the problems you might have in writing multi-threaded programs, let's answer a more simple question: why would you use threads at all? As it turns out, there are at least 2 major reasons you should use threads. The first is simple parallelism. Imagine you are writing a program that performs operations on very large arrays, for example, adding 2 large arrays together and incrementing the value of each element in the array by some amount. If you're running on just a single processor, the task is straightforward: just perform each operation and be done. However, if you are executing the program on a system with multiple processors, you have the potential of speeding up this process considerably by using the processors to each perform a portion of the work. The task of transforming your single-threaded program into a program that does this sort of work on multiple CPUs is called parallelization. And using a thread per CPU to do this work is natural and a typical way to make programs run faster on modern hardware. So the second reason is a bit more subtle: to avoid blocking program progress due to slow I/O. Imagine that you are writing a program that performs different types of I/O, either waiting to send a received message for an explicit disk I/O to complete, or even implicitly for a page fault to finish. Instead of waiting, your program may wish to do something else, including utilizing the CPU to perform computation or even issuing further I/O requests. Using threads is a natural way to avoid getting stuck. While one thread in your program waits, i.e. it's blocked waiting for I.O., the CPU scheduler can switch to other threads which are ready to run and do something useful. Threading enables overlap of I.O. with other activities within a single program, much like multi-programming did for processes across programs. As a result, many modern server-based applications, web servers, database management systems, and the like make use of threads in their implementations. Sensical. Of course, in either of the cases mentioned above, you could use multiple processes instead of threads. However, threads share an address space and thus make it easy to share data, and hence they are a natural choice when constructing these types of programs. Processes are a more sound choice for logically separate tasks where little sharing of data structures and memory is needed. In the middle of reading that, I was thinking, what is the difference in essence? In essence. In essence, the real and invariable nature of a thing. Essentially. In a sense. Yeah. It's kind of funny that they just sound similar. An example, thread creation. So let's get into the details. Say we wanted to run a program that creates two threads, each of which does some independent work, in this case printing A or B. We showed this in 26.2, page 4. The main program creates two threads, each of which will run the function myThread, though with different arguments, the string A or the string B. Once the thread is created, it may start running right away, depending on the whims of the scheduler. Alternatively, it may be put in a ready but not running state and thus not run yet. Of course, on a multiprocessor, the threads could even be running at the same time, but let's not worry about this possibility quite yet. So let's look at some code here. Including std.io, assert, pthread, common, so some common thread libraries. We have a void pointer function, myThread, taking in a void pointer arg. And it just printf. So the format string is %s new line. And we are casting the void pointer arg to a char pointer arg, returning null. Noted. And we have an int main declaring, or initializing better, two p thread t's, p1 and p2, and int rc, printing main : begin new line. We are using capital pthread create, or some wrapper around the pthread library, with the pthread t reference, null mythread a. Similarly, right under that, we're doing p2 with b. We join p1, join p2, printf main end, ret 0, Illinois. The main thread calls pthread join, which waits for a particular thread to complete. It does so twice, thus ensuring T1 and T2 will run and complete before finally allowing the main thread to run again. When it does, it will print main thread and exit. Overall, 3 threads were employed during this run: main, T1, T2. Let us examine the possible execution ordering of this little program. In the execution diagram, which is in the next figure, time increases in the downwards direction, and each column shows when a different thread, the main one, T1 or T2, is running. So we're going to look at that after reading a bit more. We're going to look at it now. So main starts running, print main begin, create T1, create T2, wait for T1. And then T1 runs, prints A, returns, and then we wait for T2, runs, prints B, returns, print main in. Could also be the case, so I thought they were running at the same time, so I don't see why they cannot be overlapping even more so. Either way, then in thread 2, the other situation is that so it can also be the case that the creation is split because it runs this. Okay, yeah. So ignoring the diagrams for a second, the ordering is not the only possible ordering. There's a bunch of different orderings. Once the thread is created, it could be run immediately. You could also see B before A. It's a bit so. As you might be able to see, one way to think about thread creation is that it's a bit like making a function call. However, instead of first executing the function and then returning to the caller, the system instead creates a new thread of execution for the routine that is being called, and it runs independently of the caller, perhaps before returning from the create, but perhaps much later. What runs next is determined by the OS scheduler, and although the scheduler likely implements some sensible algorithm, it is hard to know what will run at any given moment in time. As you also might be able to tell from this example, threads make life complicated. It is already hard to tell what will run when. Computers are hard enough to understand without concurrency. With concurrency, it gets worse. One reason why it gets worse, shared data. The simple thread example we showed above was useful in showing how threads are created and how they can run in different orders. Depending on how the scheduler tries to run them. What it doesn't show you though is how threads interact with the access. How threads interact when they access shared data. Я забыл, что моя мама сказала, что мы посмотреть как это в глаголе смотреть на совершенном виде. Посмотреть. Она посмотреть меня или мой стрим сегодня вечером. И да, я хочу сейчас чат на экране налево экрана. В левой,
В левой части экрана.
как это сказать?
В левой части экрана.
В левой части экрана. Ладно. Я хочу мычать в левой части экрана. Понятно. Ладно, да ладно. Вот. So, okay. What it doesn't show you though is how threads interact when they have access to shared data. Let us imagine a simple example where two threads wish to update a global shared variable. We're going to study the code in 26.6. Few notes. We wrap thread creation and join routines to simply exit on failure. For a program as simple as this, we might want to at least notice an error occurred, but not do anything very smart about it. So the capital P thread create calls lower P thread create and just makes sure the return code is 0. If it isn't, it prints the message and exits. Also, instead of using two separate function bodies for the worker threads, we just have a single piece of code and pass the thread as an argument. So let's see the code. So what this does, it takes an arg, casts it to a car. So it doesn't really do anything with the arg besides just print it. And we just take a counter, global counter variable, and just start adding junk to it. C volatile keyword. Wait. Dude, that's just straight up embarrassing. Getting distracted for 3 seconds and just typing discord.com. Like, what am I going to look at on discord.com? What am I doing? Concurrent. Instead of using two separate function bodies for the worker threads, we just want a single piece of code. We already talked about that. Each worker is trying to add a number to the shared variable counter and do so 10 million times. So expect 20 million. Sometimes it works. Counter 2 mil. Unfortunately, even on a single processor, we sometimes don't get the desired result. In this case, we got 1.934 mil. And yeah, we're non-deterministic, it appears. So it'll tip. Should always learn how to use new tools to help you write, debug, and understand computer systems. A disassembler shows you what assembly instructions make up the program. We used to understand the low level code and may update a counter. We run obj dump to see the assembly code. Agreed? So uncontrolled scheduling. To understand why this happens, we must understand the code sequence that the compiler generates for the update to counter. In this case, we wish to simply add a number 1 to counter. Thus the code sequence for doing something like this. Move some address, okay, the address of the counter into EAX. Add immediate 1 into EAX. Move EAX back into the counter. Then the add is performed. Yeah. Imagine 2 of our threads enter this region. That's about to increment out by 1. Then it adds it. Then a timer interrupt goes off. Saves the state of the thread to the thread's TCB. So what happened? So thread 1 loaded counter into EAX, added 1 to EAX, then a timer interrupt went off. And so the PC and the registers were saved to thread 1's TCB. Then thread 2 is chosen to run. And here's the same piece of code. Gets a value of counter, puts it into EAX. $50. And this thread 2 has EAX equals 50. Thread 2 increments it and saves it. Then you go back to thread 1 and it saves it. It just overwrote 51 with 51, so the adds were applied to 2 different. Yeah, okay. Yeah, views. The code to increment counter has been run twice, but counter, which started at 50, is now only equal to 51. So yeah, what we have here is called a race condition. more specifically a data race. The results depend on the timing of the code's execution. With some bad luck, get the wrong result. It's not deterministic, it's indeterminate. Because multiple threads executing this code can result in a race condition, we call it a critical section. A critical section is a piece of code that accesses a shared variable, or more generally a shared resource, and must not be concurrently executed by more than one thread. What we really want for this code is what we call mutual exclusion. This property guarantees that if one thread is executing within the critical section, then others will be prevented from doing so. All of these terms were coined by Dijkstra. So, tip, use atomic operations. All or nothing. It should appear as if either all of the actions you wish to group together occurred or that none of them occurred, with no in-between state visible. Sometimes the grouping of many actions into a single atomic action is called a transaction. An idea developed in great detail in the words of databases, yeah. In our theme, we'll look at synchronization primitives to turn short sequences of instructions into atomic blocks. File systems use journaling and copy on write to atomically transition their on-disk state. The wish for atomicity. One way to solve this problem would be to have more powerful instructions that in a single step did exactly what we needed to do. We needed done, and thus remove the possibility of an untimely interrupt. If you had a memory add, then that would be kind of convenient. The hardware guarantees that executes atomically. Atomically in this context means as a unit, which sometimes we take as all or none. What we'd like is to execute the three instruction sequence atomically. Move there, do this all at once. If you had a single instruction to do this, you could have done that. But in the general case, you don't do that. Imagine we were building a concurrent B tree. Atomic update of B tree. Yeah, that's a goated instruction there. If I was designing a processor, I would definitely have a atomic update of skip list instruction. Thus, what we would do instead is to ask the hardware for a few useful instructions upon which we can construct a general set of synchronization primitives. By using this hardware support in combination with some help from the operating system, we can build multi-threaded code that accesses critical sections in a synchronized manner. Reliably produces the correct result despite the challenging nature of oh my gosh, I'm cooked at reading. Challenging nature of concurrent execution. Pretty awesome, right? So this is what this section is about. One more problem waiting for another. Chapter has set up the problem of concurrency as if only one type of interaction occurs between threads. As it turns out, there's another one where one thread must wait for another to complete some action before it continues. This arises when a process performs a disk I/O and is put to sleep. When the I/O completes, the process needs to be aroused from its slumber so it can continue. In upcoming chapters, we'll study not only how to build support for sync primitives to support atomicity, but also for mechanisms to support this type of sleeping-waking interaction that is common in multiple multi-threaded programs. This doesn't make sense right now, it's okay. It will soon enough when you read the chapter on condition variables. If it doesn't by then, well, then it's less okay and you should read that chapter again until it makes sense. So some terms. Critical section is a piece of code that accesses a shared resource, usually a variable or a data structure. A race condition or data race arises if multiple threads of execution enter the critical section at the same time. Both attempt to update the shared data resource, leading to surprising outcomes. Indeterminate programs have data race conditions. the outcome is not deterministic. Avoiding these types of problems involves having threads that use multiple mutual exclusion primitives. Doing so guarantees that only a single thread ever enters a critical section, thus avoiding races and resulting in deterministic program outputs. Summary: why an OS class? The OS was the first concurrent program. That is kind of true. Imagine the case where two processes are running, assume they both call write to write the file, and both wish to append the data to the file. To do so, both must allocate a new block, record the in the inode of file where this block lives, and change the size of the file to reflect the new larger size. Because an interrupt may occur at any time, the code that updates these shared resources are critical sections. Thus, OS designers from the very beginning of the introduction of the interrupt had to worry about how the OS updates its internal structures. An untimely interrupt causes all sorts of problems, so described above. Not surprisingly, page tables, process lists, file system structures, and virtually every kernel data structure has to be carefully accessed with the proper synchronization primitives to work correctly. Indeed. So I don't care to do the pi shite. T0. These are just the codes that we discussed. pthread create, pthread join. Yeah, I could do that. You know what I mean? Quick GitHub check. Reap. Itek. Shout out Ramsey Arpasi Duso. Duso. Oh, I must just burn the shite out of my hand. Leading a research group with your wife is kind of goated, and vice versa. Teaches advanced OS. That's kind of green. Ну, это бесплатная книга, да? Что не так? This guy's kind of popular. Ekalinin. Ferret DB. Cockroach DB. So this guy's just a DB. He's a DBer. I think this guy loves DB, bro. All right, so the threads intro. Not too useful, though I am excited to be refreshed on the thread API because I haven't really touched this since last semester. And my current, I'm kind of out of a C context recently. So it would be convenient to do this so I can actually do my OS homework without getting clapped. Okay. So we're briefly covering some main portions of the thread API. Извините. All right. First thing you have to be able to do to write a multi-threaded program is to create new threads, and thus some type of thread creation interface must exist. In POSIX, it's easy. Include pthread h, int pthread create pthread, pointer to a thread. Sorry, pthread t, pointer, thread. A const pthread attribute t pointer attribute. A void pointer to a start routine. How do you say this? This is a void pointer to a function that returns a start routine. Void that takes in a void pointer. What is start routine? Are they calling it start routine as a pointer to a function that returns a void pointer? Yeah, I remember that was like a thing I had to learn a while ago, but it's just so arbitrary that I don't even remember it. And a void pointer arg. So I guess that's what you apply to this. Okay. Thread is a pointer to some type of structure. Second atcher. Stack size, priority. Which function should this thread start running in? Function name is a pointer to a function we're calling start routine, which is passed a single argument as type void pointer, which returns a void pointer. This routine required an integer argument. Set of a void pointer. Declaration would look like this, and pthread create first arg is the same. Pass in an int, and the arg is an int. Okay. Thread completion. So we just created a thread with pthread create. Now, what do you want to do if you want to wait for a thread to complete? You need pthread join with the pthread and a pointer to a pointer of the value. Just print A and B. So let's just first do this as an exercise. So we'll just write x1.c. Include pthread.h. Let's lsp stop just for no hints. Int main. We want to make a pthread tp. And we're going to make a struct. So I don't think it's type. I think it's just struct. No, it's type def struct. Type def struct here. Then you can do your alias here. So you want to alias this to be myarg1 or something, or myargt. I think it was myargt. Yeah, and then in here we'll have int a, int b. I believe that's what it was. Okay. Then in here we'll have void pointer my thread takes in a void pointer arg. Here we go. So we're making a myargt, wait, args. So we're making a myargt arg is equal to args. You're casting a myargt pointer arg. And then we're printf %d space %b new lining args a args b returning null. Make the p thread create my thread null. We give the number 1. Wait, I'm cooked. But yeah, so we want a myarg t args is equal to 10, 20. Okay, I understand that. Then we're doing the address of args. Then we're doing my thread goes here. The first one is the thread. Yeah, okay. P. We're calling this int rc. Return 1. Printf include standard h my thread. I did mean my thread. Let's check that out. Because I didn't join anything. What does pthread join take? So you just don't do the address, okay. What's the second one? Void thread return. Oh, so that's like you return something, okay. Second argument is a pointer to the return value you can expect to get back. Because the return routine can run anything. Defined as a pointer to void. My ret t returns them. So let's try this again. So we have this, and then we're going to make another struct, type def struct, both ints, int x, int y, my ret t. Okay. So he's got rvals. Does nothing with the args. So we're gonna need to make the R vowels. So let's do my ret t R vowels. Go ahead and make it a my ret t pointer R vowels. And here we'll do the address of R vowels. Printf. So we're gonna change this up a bit. %d, we're gonna do R vowels dot x and R vowels y. And we're going to free R vowels, which implies that we've malloc R vowels at some point. So we can do my ret t, which are R vowels, is equal to my ret t pointer casted with malloc times the size of R vowels. Then in here we're going to do R vowels x is equal to a. So we need that as well. Then we need my R vowels x is equal to a, and consequently R vowels y is equal to b. Then we just return R vowels. You know what I mean? And I think it's just return R vowels. So free include, or is it mem? It is include what header as malloc is standard them. Args A, args B. Oh yeah, cast to avoid pointer. Passing argument 2 of thread join with end pointer type. That's a myred t pointer pointer. Wants to be a void pointer pointer. Certainly this is myred t. Why am I so tired? Dude, what? Oh my god, I'm dumb. Hmm. Little snooze never hurt anybody. Oh my god. That is what you call a snooze right there, bro. I don't even remember falling asleep. Then in here we're gonna do R vowels. X is equal to A. So we need that as well. Then we need my R vowels. X is equal to A. And consequently R vowels Y is equal to B. Then we just return R vowels. You know what I mean? I think it's just return R vowels. So free include, what is it, mem? It is include what header as malware is standard them. Args A, args B. pass to a void pointer. Passing argument 2 of thread join with pointer type. That's a myred t pointer pointer. Wants to be a void pointer pointer. Certainly this is myred t. What was I doing right here? Oh my gosh, I'm cooked. I was actively falling asleep while I did this. That's one. Why am I so tired? Dude, what? Oh my god, I'm dumb. No way, I just fell asleep. Oh my god. Dude, that's so crazy. I keep accidentally falling asleep. Shut up. Dude, that's so crazy. Yeah, I don't think I have anything. I think I'm just dumb, Moki. I think I'm probably just stupid. You know what I mean? Okay, well, let's return to this. Oh, maybe like put something in the. I swear I get good sleep. Like I've been on a sleep schedule for 2 weeks at this point. Это мой брат. All right, one sec. Better shut up and read. All right. So you can't just initialize it like that. You have to use the pthreads mutex initializer, or you do pthread mutex init. Assign that to an int. Assert RC is non-zero. Assert RC is 0, sorry. Probably just inline that, yeah. Try walk and timed walk, which I haven't used. Condition variables. So you got cond wait, taking in a condition in the mutex, and signaling the condition. Set cond wait puts a calling thread to sleep and thus waits for some other thread to signal it. Usually when something in the program has changed, like that the now sweeping thread might care about. Typical usage looks like this. Initialize the lock, initialize the condition, acquire the lock, while ready is equal to 0. I don't remember what ready would be in this case. While ready is equal to 0, pthread cond wait, so await the condition, and that also frees up the lock. And then when ready is not 0, see, I don't really recall how that would work. After initialization of the relevant locking condition, a thread checks to see if the variable ready has yet to be set to something other than 0. Not thread simply calls a wait routine in order to sleep until some other thread wakes it. The code to wake a thread. Oh, okay, so there's other code waking thread. Okay. The code to wake. So this is like some global shit. The code to wake a thread. Should run on some other thread looks like this. Pthread mutex lock, the lock. Ready is equal to 1. Signal the condition and unlock it. Always have to hold the lock when you signal. Second, you might notice that the wait column takes a lock as its second parameter. Whereas the signal only takes one condition. The reason for this difference is that the wait call, in addition to putting the call to sleep, releases the lock, yeah. Before returning after being woken, wait reacquires the lock, thus ensuring that any time the waiting thread is running between the lock acquire at the beginning of the lock. The waiting thread rechecks the condition in a while loop instead of a simple if state. We'll discuss this issue in detail when we study condition variables in a future chapter. Although it rechecks the condition, adding little overhead, there are some pthread implementations that could spuriously wake up a waiting thread in such a case. Without rechecking the waiting thread, we'll continue thinking that the condition has changed even though it's not. Huh. It is safer thus to view waking up as a hint that something might have changed, rather than an absolute fact. Note that sometimes it is tempting to use a single flag to signal between two threads instead of a condition variable associated lock. For example, we could rewrite the waiting code to look like this while ready equals 0 spin. Don't do this. Waste CPU cycles. Error frown. Don't use ad hoc synchronization. You must have the header pthread. We've introduced the basics of the pthread library. Mutex is via lock, signaling, and waiting. You don't need much else to write robust and efficient multi-threaded code except patience and a great deal of care. And on the chapter with a set of tips that might be useful to you when writing multi-threaded code. There are other aspects of the API that are interesting. Man-K. What does -K do? Man, what does -K do? Oh my god. Man pthread. Man-K pthread. Man-K. Propose what? -K. Global apropos? What is that? What is that, bruh? Yeah, this is not 1900. I don't know what you're talking about over. No, that's kind of goated. Report bugs to CJ Watson at Debian.org. I mess with that. Bro, man maintains man. That's kind of good. Oh, that guy's kind of good. All right. Thread API guidelines. So keep it simple. Minimize thread interactions. Initialize locks and condition variables. Check your return codes. Be careful with how you pass arguments to and return values from threads. So yeah, use heap. Each thread has its own stack. Always use condition variables and use the man pages. Let's look at locks, the largest chapter, perhaps in the entire kniga. Wait, let me hit a casual clean sesh. Well, no reason to continue, or to every reason to continue. Interesting. From the introduction to concurrency, we saw one of the fundamental problems in concurrent programming. We'd like to execute a series of instructions atomically. Due to the presence of interrupts on a single processor, we couldn't. This chapter, we thus attack the problem directly with something called a lock. Did we not just do this? Programmers annotate source code with locks, putting them around critical sections and thus ensure that any critical section executes as if it were a single atomic instruction. The basic idea: we want to increment a bounce. So we have some globally allocated lock mutex. We lock the mutex, perform our operation, and unlock the mutex. A lock is just a variable, and thus to use one, you must declare a lock variable of some kind, such as mutex above. It holds the state of the lock. It is either available /unlock /free or acquired /locked /held. Semantics of the lock and unlock routines are simple. Calling the routine lock tries to acquire the lock if no other thread holds the lock. The thread will acquire the lock and enter the critical section. This thread is sometimes said to be the owner of the lock. If another thread then calls a lock on that same lock variable, mutex here, it will not return while the lock is held by another thread. In this way, other threads are prevented from entering the critical section while the first thread holds the lock is in there. Once the owner of the lock calls unlock, the lock is now able to free again. If no other threads are waiting for the lock, the state of the lock is simply changed to free. If there are other threads stuck in lock, one of them will notice this change, acquire, and enter. They provide some minimal amount of control over scheduling to programmers. In general, we view threads as entities created by the programmer but scheduled by the OS in any fashion the OS chooses. Locks yield some of that control back to the programmer by putting a lock around a section of code. The programmer can guarantee that no more than a single thread can ever be active within that code. Thus, locks help transform the chaos that is traditional OS scheduling into a more controlled activity. P-thread locks in particular. Perhaps POSIX locks is the P. They call them a mutex. Provides mutual exclusion between threads, i.e. if one thread is in the critical section, it excludes some others from entering until it has completed the section. So when you see the pthreads code, it's doing the same thing. You initialize a lock, acquire the lock, perform your operation, and release the lock. Different locks should protect different variables. More fine-grained approach. So building a lock. Okay, so this chapter is actually useful. So how do we build a lock? What hardware support is needed? What OS support? So that's where we're going on from here. To build a working lock, we will need some help from our old friend, the hardware, as well as our good old pal, the OS. Over the years, a number of various hardware primitives have been added to the instruction sets of various computer architectures. That we don't care as much about. We'll study how to use them in order to build a mutual exclusion primitive like a lock. We also study how the OS gets involved to complete the picture and enable us to build a sophisticated locking lid. Evaluating locks. Before building any locks, we should first understand what our goals are in this ask. I'm going to shut up and read. int tested set, int old pointer, int new. Get the value at old pointer. Store new into old pointer. Return old. I don't really understand that. So we're going to read this and then go back up. Let's just stop and read this. Decker's and Peterson's algorithms. So it atomically returns the old value pointed to by old pointer and updates old pointer to new. Huh. Init lock flag 0. To lock it, so you spin wait while test and set the flag to 1. So until something else. So you keep setting it to 1 until you read that it's 0. And that means another thread came in and called unlock. Okay. And this works because you can reset it and read it in one instruction. So instead of them both setting it on one instruction and then both reading it, that's all at one time. Okay. So correctness, it must work. Then fairness. And performance. What is the overhead? So we also have compare and swap. Some pseudocode with a pointer, expected and new, into original is the value at the pointer. If original is the expected, set it to the new, and then return the original. While compare and swap, lock flag 0. So see if it's 0. If it is, set it to 1. And then if it keeps returning 1 spin, let's return 0. So what's the difference? Well, this will be useful in my lab. Compare and swap pointer, old new. Excuse me. Lock-free synchronization. Okay, so there's more interesting lock tactics. They use it, but for now it is identical behaviorally. Load linked and store condition. So now we're getting into stuff I don't really know as much about. Nice. Some platforms provide a pair of instructions that work in concert to help build critical sections. On MIPS, load linked, store conditional. Build in tandem, locks, and other concurrent structures. arm as well. Load linked fetches a value from memory and places it in a register. Key difference comes with the store conditional, which only succeeds it only succeeds and updates the value stored at the address just loaded from if no intervening store to the address has taken place. In the case of success, the store conditional returns 1 and updates the value at pointer to value. If it fails, the value at pointer is not updated and 0 is returned. So how would I build a lock using this? Keep loading. So in your loop, you want to load. If it's 0, store 1. Start with a load, store, keep trying to store 1, and I'm talking about in lock. Load, keep trying to store 1. Or keep trying to store your thread ID maybe. And if you get 1, go in. And just keep waiting until you do that. First, our thread spins, waiting for the flag to be set to 0. Okay, so I was just completely wrong. You spin waiting for load to return 0. Then you try to acquire the lock via the store conditional. If it succeeds, the thread has atomically changed the flag's value to 1. Notice how the failure might arise. One thread calls lock and executes the load linked. Turning 0. One thread calls lock. Executes load link, returning 0 as the lock is not held. Before it can store, it's interrupted and another thread enters the lock code. Also executing load link and getting 0. You continue at this point, 2 threads have each executed the load link, each are about to store conditional. Only one of them will update the flag to 1 and acquire the lock. Yeah, the one that doesn't win will fail. I'll have to try again. Oh, he's like older now. Older. So while 1. While load linked, lock flag is equal to 1. wait until it's 0. If store conditional, storing 1 in there is successful, return. Otherwise, try again. In other words, while a load linked so if it's 1 spin, and if the store conditional is 0 spin. Yeah, okay, let's show. One final hardware primitive is the fetch and add instruction, which atomically increments a value while returning the old value at a particular address. Interesting. The C pseudocode for the fetch and add instruction looks like this. Int old equals pointer deref. Pointer deref is equal to old plus 1, return old. So it atomically increments a pointer and returns its old value. Instead of a single value, this solution uses a ticket and turn variable in combination to build a lock. When a thread wishes to acquire a lock, it first does an atomic fetch and add. That value is now considered the thread's turn. So the lock turn is used to determine which thread's turn it is. When my turn equals turn for a given thread, it is that thread's turn to enter the critical section. Unlock is accomplished simply by incrementing a new turn, such that the next waiting thread, if there is one, can now enter the critical section. Wait, so how do you lock it? When a thread wishes to acquire a lock, it fetch and adds on a ticket value. I don't understand that at all. What it gets here is its value. How does this ever decrement? You increment the turn such that the next waiting thread. Wait, what? How does how does that work? That doesn't make any sense. So you keep incrementing it. Okay, you increment it once. Your ticket is as far away from the current value as possible. I'm gonna ask ChatGPT. So I'm not understanding, bro. Here's a pseudocode. You have a ticket and a turn. When you lock it, my turn, fetch and add, you lock the ticket. So the ticket. So what's my turn? So my turn is equal to the previous ticket, and then you just incremented it. While lock turn is in my turn, so Ticket is the next available ticket number that a new contender will take. Turn. This indicates the current ticket holder allowed to enter the critical section. Lock acquisition. Increments the ticket. Because ticket leads turn. It increments ticket. So every time you want to lock, it increments the ticket for the next thing to lock. And the turn. And then when you unlock, it increments the turn. Is that how that works? Yeah, okay. That makes sense. Each thread spins until the turn. You get a unique ticket by incrementing ticket. Or you get a turn. So say you're the first process. Starts at 0, 0. So your ticket is 0. The next ticket is 1. Sorry, your turn is 0. The next ticket is 1. So you get the lock because your turn is this lock's turn. You do your thing and then you unlock. And so now turn is 1. So then the next ticket, or you increment turn. And so the second thread to come in got the lock, incremented the ticket to 2. Okay, that's chill. Too much spinning. You need OS and hardware support. Just yield. What do you do when a context switch occurs in a critical section? Wait, I thought that didn't happen. What? Huh? I thought that literally confirmed didn't happen. I thought it was all atomic. What happens when a context switch occurs in a critical section? The threads start to spin endlessly, waiting for the interrupted thread. Wait. Okay. Convoy. Okay. Lock convoy. Okay. Okay, that makes sense. So it can still be context switched. And then the threads are all waiting, even though it's not even running. Okay. When you're going to spin, instead, give the CPU to another thread. Just yield. So the flag is 0. While testing the set. So how does this work again? You see what the flag is. And then you keep setting it to 1, and then if you get a 0, then you unlock. You just yield. So if you get 1, you just yield. It just gives up the CPU. Deschedules itself. Think about the example with 2 threads on 1 CPU. In this case, our yield-based approach works quite well. If the thread happens to call a lock and find a lockout, it will yield the CPU, and thus the other thread will run and finish its critical section. There are many threads. One thread acquires the lock and is preempted. The other 99 will each call a lock. It's a bit better. Kind of wasting the context switch does not address starvation. Thread may get caught in an endless yield loop while other threads repeatedly enter and exit. Address starvation directly using queues, sweeping instead of spinning. The real problem with some previous approaches, other than the ticket lock, is that they leave too much to chance. The scheduler determines which thread runs next. If the scheduler makes a bad choice, a thread that runs must spin or yield the CPU immediately. Either way, there is a potential for waste and no prevention of starvation. So we'll come back to this. Okay, no, we're just going to read it. So you have a flag, a guard, and a QT, pointer Q. So init, flag 0, guard 0, Q init, M Q, M to Q. Q init, M Q. M dot Q. So you're getting the lock of the, say, I have no idea what that is. Lock T. So if you want to get the lock, while test and set guard. So you have like 2 locks, yeah. First you want to get the guard. So while you can't get the guard using test and set because that'll return 0 when it's 0. And then but you're setting it to 1. So until something else sets it to 0, it's just going to be 1. Once you get the lock, so I'm going to need some explanation. If the flag is 0, set the flag to 1, so acquire the lock. Set the guard to 0. Acquire the lock and release the guard. Otherwise, so you can't grab the lock. So you're going to want to add your ID to the queue and set the guard to 0. And that's something else getting here. And then you're going to park. Okay. So then you're going to unlock. So you function unlock. So when you have the lock and you want to unlock it, wait to get the guard. So wait to make sure nothing else is actually locking it. If the queue is empty, let go of it. Otherwise, unpark the queue, top of the queue. Okay. So that's kind of, okay. So in summary, what does this do? this works by having a lock on putting yourself on the queue, and then on unlock the thread that has the lock will look to the queue. The queue is empty, it'll just open the lock so that the next thing to call lock can just grab it immediately. Otherwise, it will look in the queue to find which has been waiting the longest for the lock and give it to that. Okay. Park puts a thread to sleep, and unpark thread ID to wake a particular thread as designated by thread ID. These two routines can be used in tandem to build a lock that puts a caller to sleep if it tries to acquire a held lock and wakes it when the lock is free. Let's look at the code in 28.9 to understand one possible primitive. More reason to avoid spinning priority inversion. So T2 is more important. A higher priority thread waiting for priority inheritance. I read about that. There's still some spin rating to get the queue lock. What would happen if the release of the guard lock came after the park? Your machine would do nothing. You're never gonna, because you need the guard to be 0 to get into here, so you're never even gonna get anything off the queue. It's just gonna be in here the whole time. You're just gonna be sitting here for 20 hours. The flag does not get set back to 0 when another thread gets woken up. Huh. Just before the call to park. With the wrong timing, a thread will be about to park assuming that it should sweep until the lock is no longer held. A switch at that. If the thread then released the lock. So if we were here, another thread released the lock. I don't see that. A thread is about to call park on the assumption that it should sweep until the lock is released. The sequence of events can lead to a situation where the wake-up signal could be missed, causing the thread to sweep indefinitely. I don't see it. Focusing on the queue add. So you add yourself to the queue. Oh, and then something unparks you before you park. Okay. Thread A arrives at the point where the lock is held. It executes, adds itself to the queue, releases the guard. Then a context switch occurs and it runs unlock. Now A is in the queue, unparked, and B acquires the guard, finds A waiting in the queue, unparks A, and then A parks itself and it's not in the queue. Okay, I see. So you need something that sets the guard and park at the same time, I believe. A thread can indicate that it is about to park. If it then happens to be interrupted and another call calls unpark before park is actually called, the subsequent park returns immediately instead of sleeping. Okay. Different OS, different support. Linux provides a futex, which is similar to the Solaris interface, but provides more in-kernel functionality. Each futex has associated with it specific physical memory location, as well as a per futex. So what is a futex? In kernel queue, callers can use futex calls to sleep and wake as need be. Specifically, two calls are available. The call to futex wait address expected puts the calling thread to sleep, assuming the value at the address is equal to expected. If it is not equal, the call returns immediately. The call returns immediately. The call to the routine futex wake address wakes one thread that is waiting on the queue. The usage of these calls in a Linux mutex. Using a futex on a mutex, bruh? What is it? The code snippet is from low-level lock.h in the nptl library, part of the GNU libc. Uses a single integer to track both whether the lock is held or not, the high bit, and the numbers of waiters on the lock, all the other bits. Thus, if the lock is negative, it is held. Second, the code snippet shows how to optimize for the common case, specifically when there is no contention for the lock, with only one thread acquiring and releasing the lock. Very little work is done. The atomic bit test and set to the lock. The atomic bit test and set to lock, and an atomic add to release the lock. See if you can puzzle through the rest of this real-world lock to understand how it works. Do it and become a master of Linux locking, or at least somebody who listens when a book tells you to do something. Okay, so let's inspect this. So mutex lock with a mutex int v. Bit 31 was clear. We got the mutex fast path. If atomic bit test set mutex 31 is equal to 0. Fast user space mutexes that combine user space atomic operations with kernel-based waking mechanisms to implement efficient locks. They aim to keep uncontended locking operations entirely in user space for speed, resorting to system calls only when necessary to wake or wait threads. The provided pseudocode demonstrates a possible implementation of a futex-based mutex. The mutex is represented as an int where bit 31 is whether it's held. The lower 31 bits act as a counter of waiters. So mutex lock. So lines 3 to 5, the lock attempts to set bit 31 atomically. So set bit 31 to 0. So set bit 31 high. If it was 0, attempts to set bit 31 to 0, to 1. So it attempts to set it to 1. If it was 0, then you acquire the lock and you return. Otherwise, if the fast path fails, you increment the mutex counter using atomic increment mutex. So you're one more dude waiting on the lock. Wait loop. You enter a loop checking if you can get it. So while 1. So this is like the fast path, yeah. You don't, okay, yeah, that's true. If atomic bit set mutex 31, so you keep trying to set it to 0. No, you keep trying to set it to 1, and if it is 0, then you decrement that you're even waiting on it, because you don't have to actually increment you're waiting on it if it's just ready. So you try to set the bit high. If it is low, that means you got the lock, so you decrement that you're waiting and return. If you can't do that, you read the current value of mutex into v, have to wait first to make sure mutex value we are running is negative. So read the current value of the mutex, which we've been just incrementing for 20 years. Into v. If v is non-negative, that means it's if v is positive, that means the lock is not held. If he is negative, it means the lock is held and there are waiters. So if mutex wait. Mutex wait puts the thread to sleep until the mutex value at mutex changes from v. So until another lock is there, I guess. Mutex unlock. So if the first bit is a 1, clears bit 0, clears bit 31 and checks if the result is 0. If the result is 0, so that only occurs if there are not other interested threads. Okay, so if there's no threads waiting, just return. If there are threads waiting, wake the mutex. Noted. Two-phase locks. Has the flavor of an old approach that has been used on and off for years. Going back to DOM locks in the 60s, now referred to as two-phase locks. Realizes that spinning can be useful, particularly if the lock is about to be released. In the first phase, the lock spins for a while, hoping that it can acquire it. It's not acquired during the first spin phase. A second phase is entered where it's put to sleep and only woken up when it becomes free later. The Linux lock above is such a form of above is a form of such a lock. It only spins once. The generalization of this could spin in a loop for a fixed amount of time before using mutex support to sleep. Two-phase locks are yet another instance of a hybrid approach where two good ideas may indeed yield a better one. Depends strongly on many things, hardware environment, number of retailers. Summary. Park unpark, mutex Linux. Okay. So that was a lot. That was the longest chapter so far. Dude, persistence is going to be rage bait. But let's move to locked data structures. And I'll probably go to the bathroom here. Streaming for 3 hours. I've returned. Curious what time it is. I kind of feel like doing something. It's not just sitting here for the next 3 hours. Hmm. Well, let's just shut up and start reading more. Okay, locked base concurrent data structures. Counter has a value. Increment, decrement, initialize it to 0 and get a value. Okay. It's concurrent? Wait, is this a concurrent one? I guess it is. No. Wait. No, it's not concurrent. Yeah, I don't think this is concurrent. Am I tripping? 29.2 shows how you could do. Yeah, okay. I was gonna say what? Add a single lock. Release when returning from the call. Similar to a data structure built with monitors where locks are acquired and released automatically as you call and return from object methods. At this point, you have a working concurrent data structure. You might have a performance problem though. If data structure is too slow, you'll have to add more than just a single lock. If it's not too slow, it's done. I'm going to benchmark. More CPUs active. So now our counter has a mutex in it. Init it. Init the mutex as well. Incrementing. Acquire the lock, increment, release the lock, acquire the lock, release the lock, acquire the lock, release the lock. Cool. So where's the figure of the... Really like to see the threads complete. Okay, so what's this? Time. This is the amount of processors. Amount of processors. 5 to 0. What is 5 to 0? Single thread can complete the million counter updates in a tiny amount of time. Having 2 threads each update the counter 1 million times takes over 5 seconds. What is G? Dude, what is all this, bro? What happened to saying precise, the top line in the figure labeled precise? No way, he's talking about something 8 pages down. What is that? Dude, why are you referring to something 20 pages away? So yeah, it just takes forever. Okay. Oh, whatever. So they've studied how to build more better ones. One is the approximate counter, representing a single logical counter via numerous local physical counters and a global counter. Machine with 4 CPUs, there are 4 counters and 1 global one. Shut up. In addition to these counters, there are also locks, so 1 for each local counter and 1 for the global counter. When a thread running on a given core wishes to increment the counter, it increments its local counter. Access to this local counter is synchronized via the corresponding local lock. Because each CPU has its own local counter, threads across CPUs can update local counters without contention, and thus updates to the counter are scalable. However, to keep the global counter up to date, in case a thread wishes to read its value, the local values are periodically transferred to the global counter. By acquiring the global lock and incrementing it by the local counter's value, the local counter is then reset to 0. How often this local to global counter transfer occurs is determined by the threshold S. Smaller S is, the closer it is to the non-scalable one, the bigger S is, the more scalable, but the further off it might be. One could simply acquire all the local locks and the global lock to get an exact value, but that is not scalable. To make this clear, let's look at an example. In this example, the threshold S is set to 5. There are threads on each of 4 CPUs updating their local counters at 1.4. The global counter value G is also shown in the trace, with each time increasing downward at each time step. Local counter may be incremented if the local value reaches the threshold S. The local value is transferred to the local counter, and the local counter is reset. The lower line shows you all the S's. Performance is excellent. Time taken to update the counter 4 million times on 4 processors is hardly higher than the time it takes to update 1 million times on 1 processor. Okay. So you got an array. So you have the local counts, array of the locks, threshold, init record threshold, init locks, init values of all local counts and global count. Void init, counter C and threshold, C threshold, threshold, C global 0, P thread, Glock. I want a Glock, dude. Counter T. So this is just to pass the struct in to initialize it. Suppose that makes sense. For the number of CPUs, set it to 0 and you can get in it. Update, usually just grab local lock and update. Once it has version threshold, grab local lock. So thread ID amount and CPU is the thread ID percent the num CPUs. Thread ID mod num CPUs. I don't understand that. But we have the CPU index. So lock the local mutex. If it's above the threshold, lock a global one as well and update it. Release it, set the local to 0, and then unlock the local. Get, just return the global amount, lock the global. Temp the global, release the global, return the global, save. And so, as you increase your approximation, it performs solidly enough. More concurrency isn't necessarily faster, indeed. Concurrent linked lists. node has a key and a next pointer. So each list has a head and a lock. You initialize the list, putting in a list. Set the head to null. Initialize the mutex, makes sense. So inserting. You need the list lock. I thought we just said you don't need to do this. I thought you could malloc the node first. Yeah, what? Okay, so I'm not even reading that one. So you malloc the node first. Error, if there's an error, return early. Set the key of the node, so do everything in the node and just lock the critical section, which involves inserting at the new head. Okay, so it's just inserting at the head. Oh my god, freak this bug, dude. Inserting at the head, set the head to new, and then unlock, return 0, list lookup, return value 0, sorry, -1. Lock it, get the head, while cur next, cur key, return value 0. Now both success and failure. So this is just either way. So okay, that's kind of smart. Scaling linked lists. It does not scale well. You can enable more concurrency within a list using hand-over-hand locking, aka lock coupling. The idea is pretty simple. Instead of having a single lock for the entire list, you can set out a lock per node of the list. When traversing the code, the list first grabs the next node's lock and then releases the current node's lock. Okay. Be wary of locks and control flow, a general design tip, which is useful in concurrent code as well as elsewhere. Just be wary of control flow changes that lead to function returns, exits, or other similar conditions that halt the execution of function. Particularly exceptional returns. Frick exceptions, honestly. As many functions will begin by acquiring a lock, allocating some memory, or doing some other similar stateful operations. When errors arise, the code has to undo all the state before returning, which is error. Conceptually, a hand-over-hand linked list makes some sense. Where's the hand-over-hand linked list? It enables a high degree of concurrency on list operations. However, in practice, it is hard to make such a structure faster than the simple single lock approach, as the overheads. What's the next chapter? Condition variables and semaphores. Okay. However, in practice, it is hard to make such a structure faster than the simple single lock approach, as the overheads of acquiring and releasing locks for a single node for each node of which traversal is prohibitive. Rip reading. Yeah, each node is kind of crazy. Concurrent queues. As you know now, by now, there is a standard method to make a concurrent data structure. Add a big rock. Slightly more concurrent queue designed. The data structures in code for this queue are found on page 11. There are 2 locks, one for the head of the queue and one for the tail. The goal of these 2 locks is to enable concurrency of NQ and DQ operations. In the common case, the NQ routine will only access the tail lock. In DQ, only the head lock. One trick is to add a dummy node allocated in the queue initialization code. This dummy node enables the separation of the head and tail operations. Study the code, or better yet, type it in, run it, measure it, and understand how it works deeply. Queues are commonly used in multi-threaded applications. However, the type of queue used here with just locks often does not completely meet the needs of such programs. A more fully developed bounded queue that enables a thread to wait if the queue is either empty or overly full is the subject of our intense study in the next chapter on condition variables. Watch for it. Okay, so that's kind of useful. So here is the Michael and Scott concurrent queue. So you have a int value, struct node t next. So that's each node. Okay, that's easy enough. Then the queue itself has 2 mutexes, the head lock and the tail lock. Head and a tail pointer. Okay. Queue init. So the queue temp. So malloc the dummy node, it appears. Temp next null. Queue head, queue.temp. No. Head. Temp is a new node. Temp next. head and tail both point to temp. And knit both the locks. Okay. So in queuing, make a temp, serve that it malloc properly, set the value, next null, acquire the lock. So this puts it at the end. Tail next temp, tail temp. Tail next temp. The tail is temp, yeah, I agreed. Unlock, DQ. So acquire the lock. Temp. So take the head. New head. Okay, yeah. Take the head off. Set the new head to the next of the previous head. If new head null, return -1 because the queue is empty, but return the lock first. Otherwise, int value, so it's passing a value, so it's set the value. And queue head, obviously passing the queue. So new head, previous head value, new value, head value. Pthread, unlock the mutex, free temp. So free the old head, okay. So a concurrent hash table, okay. So 101 buckets. So your hash T is a list T. Okay, so it's a list-based collision. List of buckets. So 101 buckets. Hash init with a hash T pointer. Int I. And for, I don't know why you just don't do the int on the same line. Interesting. So for all the buckets, initialize the lists. So that's using this thing we just talked about. All right, and so hash insert a key. You just run a list insert on the bucket with the key, okay? Doesn't resize. Left as an exercise for the reader, you love to see it. Straightforward, just built on the list. Good performance. Instead of having a single lock, it's a lock per bucket. And so summary, we introduced sampling of current data structures. A few important lessons along the way. Be careful with acquisition of locks. Run control flow changes. Last point, avoid premature optimization. Scratch the surface. There's a survey with more information. Interested in particular concurrent data structures. In the case of B trees, probably likely talking about databases. You also might be curious about techniques that don't use traditional locks at all, such as non-blocking data structures, something we're going to taste of in the chapter on common concurrency bugs. But frankly, this topic is an entire area of knowledge requiring more study than is possible in this humble book. Knuth's law. There we go. Green. Maybe early optimization. A single lock for the whole OS is devious. Next, condition variables. Hopefully this is short. Ooh. But after this, we have semaphores, which is the chapter that I need to read the most, apparently. Currency bugs and event-based concurrency. Yeah, I need to read these three as well. All of these are quite useful. So I'll continue. Dang, I haven't had a viewer in like weeks. The amount of time I sat in this chair reading on the screen is immense. The amount of time I've spent looking at this monitor. I've had this since sophomore year of high school. I'm currently a junior in college. That's 5 years. If I look at it for 5 years times probably an average of 5 hours a day, including times when I just wasn't here for months at a time. 5 times 5 times 365. 9,000 hours looking at this. Feels like it's been more than that. 5 years times 365 times 5. 10,000 hours. So how many days is that? So 10,000 hours divided by 24. Oh. Yeah, I guess it is a lot of days. An entire year consecutively looking at this. That's wild. That's crazy. That's insane. That's crazy. Condition variables while I have my thing in the fryer, Tsipa. I just got a new subscriber. Thank you. Whoever that is. Condition variable is used to allow threads to wait for certain conditions, so always used in conjunction with a mutex. Thread that waits for the condition. Lock the mutex. Okay, yeah, that's true. Lock the mutex, check a condition in a loop. If the condition isn't met, wait on the condition variable, which atomically releases the mutex. Okay, so I think we're gonna read. Excuse me. Explicit queue that threads can put themselves on when some state of execution is not desired. Is not as desired. Wait. Damn. A condition variable is an explicit queue that threads can put themselves on when some state of execution, some condition, is not as desired. Is not as desired. It's not in a desired state. Okay, that's true. Some other thread, when it changes said state, yeah, I don't, okay, whatever. Some other thread, when it changes said state, when some state of execution is not as desired. Okay. Some other thread, when it changes said state, can then wake one or more of those waiting threads and thus allow them to continue. Yeah, that's true. By signaling on the condition. The idea goes back to Dijkstra's use of private. Bro, this is what I said. Bro, I'm about to rage. The idea goes back to Dijkstra's use of private semaphores. Similar idea was later named a condition variable by Hoare in his work on monomers. Okay. To declare such a condition variable, use the pthread T C type. Declares C as a condition variable. Proper initialization is also required. A condition variable has two operations associated with it, wait and signal. The wait call is executed when a thread wishes to put itself to sleep. Cool. Signal call is executed when a thread has changed something in the program and thus wants to wake a sleeping thread. So pthread cond wait, pointer mutex. So it releases the mutex and then until signaled recaptures the mutex. And pthread cond signal, assuming you already have the mutex, signals that condition. Okay. So let's revisit this. So we have an int done is equal to 0. Let's first look at the functions. Or either way, we can look at these first. We have done 0, mutex am init, con c init, threxit, start at main. We have a parent making a pthread p. We are creating it with this child function. We're joining it, printing parent, returning it. So third join. Okay. So let's look at the child, yeah? We create this process, this thread, sorry. Thread with arg null, print child, Brexit, return null, Brexit, lock the mutex, set done to 1, signal C, why do you need the done? I thought the point of the con was so you didn't have to do this. Why do you need the done? Let's ask Jibbity. Even though condition variables are used to avoid busy wait spinning, they don't inherently remember the state of an event.
they simply notify waiting threads that something may have changed. You still need a separate flag like done to record the actual state change. No, I actually kind of like Jippity runoff. I'll read more. Okay. So you see them as wait and signal for simplicity. Wait calls that it also takes a mutex. It assumes that this mutex is locked when wait is called. Indeed. Responsibility of wait is to release the lock, release the mutex, and put the calling thread to sleep atomically. When the thread wakes up after some other thread has signaled it, it must reacquire the lock before returning to the caller. This complexity stems from the desire to prevent certain race conditions from occurring when a thread is trying to put itself to sleep. Let's take a look at the solution to the join problem, figure 33. This is 33. Okay, so with that in mind, there are two cases to consider. In the first, the parent creates the child thread, but also parent creates a child thread but continues running itself. Parent creates a child thread but continues running itself. Thought I was joining. Thought we were joining and waiting for done to equal 0, or done to equal 1. Oh, so this is like instead of looping. Oh, okay, that's true. That's true. So instead of looping, this will like wake up when this is signaled, and then it'll see done, not 0. Okay, that's true. And then unlock the mutex. That's true. That's true. All right. 8 subs? No, I'm actually hyped to have 8 subs. Shout out having 8 subs, dude. Where was I at? Parent creates a child but continues running itself. Thus immediately, oh, okay, so one processor. Thus immediately calls into thread join to wait for the child thread to complete. In this case, it will require the lock. Check if the child is done. It's not. Put itself to sleep by calling wait, releasing the lock. Then the child will run. Print the message child, call threadexit, wake the parent up. Then grab the lock, set the state. So threadexit grabs the lock, sets this state variable done, signals the parent, waking the parent. Then the parent will run, returning from wait with a lock that would unlock the lock and print end. In the second case, the child runs immediately upon creation, sets done to 1. So let's look back at that. The child, so imagine here, and the child just starts running. So the child prints child, and exits, grabs the mutex. Sets done to 1, signals it, unlocks the mutex. Then we go to thread join, lock the mutex. We don't even go in here because done is in 0, and then we unlock the mutex. Okay, so we just lock the mutex and do nothing effectively, but not too bad in principle. This does not wait and returns, yeah. Parent uses a while loop instead of just an if statement. While this does not seem strictly necessary, it's always a good idea to make sure you understand the importance of each piece. It's already done. Just make sure you understand. Okay, so we'll come back to this. Let me get my food. Rather modest meal today. 2 Costco chicken fillets, some chili sauce. And the bev today is going to be a tonic water. Pretty splendid. Splendid meal, honestly. So let's find something to watch as we do. Hmm. Prime is just kind of annoying these days. I'm not gonna watch this, but shout out JV Schultz for using Groovebox on Arch Linux on a ThinkPad. Like a G. In hindsight, that maybe wasn't a ThinkPad, it just had the same aesthetic. Bro, why is YouTube so shite? Holy guap. You're looking at the recommendations, starting eating because it's just garbage, man.
Problem is, there's almost nothing useful you can actually learn in like a 10-minute video. So much garbage, dude.
У тебя есть какие-нибудь фобии?
I'm
Может
just
быть,
studying
ты
Russian at this
боишься
point.
темноты, высоты или воды? Есть какие-то индивидуальные, нетипичные, необычные страхи?
Страхи. Наверное, нет. Наверное, нет. В детстве, когда я была маленькой, у меня была фобия акул,
М,
потому что я очень любила смотреть фильм «Челюсти».
мгм,
О.
Любила и боялась. Боялась и любила.
мгм,
И я очень долго боялась открытой воды, особенно моря.
мгм,
Мне казалось, что там обязательно есть акулы. Но любовь к плаванию победила этот страх. Я очень люблю плавать. И я очень люблю плавать именно в открытой воде. Я не люблю бассейны,
мгм,
потому что в бассейне там линии и стены.
мгм,
А я люблю плыть вперед, вперед, долго-долго. И просто в какой-то момент я поняла, что нету акул обычно. Ну, в Черном море
м.
вроде нет.
Не должно быть.
Слово
Не
«нету»
должно
интересно.
быть. Да и в других морях
Нет.
очень малая,
Мгм,
маленькая
Интересная,
вероятность встретить
можно сказать.
акул.
мгм,
А сейчас, наверное, нету у меня каких-то фобий.
Нет, у меня как-то...
Конечно, если я вдруг неожиданно увижу какое-то неизвестное мне насекомое
мгм.
или крысу. Нет, крысу я не боюсь.
А пауков?
Ну, в России вообще нету ядовитых пауков.
Мгм,
У нас все пауки добрые,
мгм,
безобидные. И я всегда знала это, поэтому нет, пауков я не боюсь. Чего еще бояться обычно? Клаустрофобия?
Темноты.
Вроде нет. Нет, темноты не очень боюсь. Нет, не боюсь.
Мгм. Окей.
Высоты, конечно, мне дискомфортно на большой высоте.
Мгм,
Я могу немножко нервничать, но это не ужасная фобия.
мгм, мгм. Я понял. Хорошо. Инна у нас бесстрашный и смелый человек.
Типа
Взрослый,
того.
зрелый человек, который ничего не боится. Очень
М.
хорошо. Очень хорошо. И я думаю, так и должно быть у здорового взрослого человека. Не у меня. Окей.
А у тебя есть фобии?
Небольшие, да, но давай сегодня не будем говорить обо мне, побольше послушаем о тебе. Как-нибудь в другой раз, может быть, расскажу, потому что я тоже люблю много говорить. Давай другой вопрос, другая тема, если это не секрет. Я знаю, что в разных культурах и просто разные люди не очень любят отвечать на этот вопрос, а в некоторых странах, может быть и в нашей стране тоже, это иногда считается неприличным вопросом.
Мгм.
Инна, ты религиозный человек? Какие у тебя отношения с религией, с Богом и какое место в твоей жизни занимает эта тема?
Я выросла в православном обществе,
Православным я не знаю.
в
Я не понял.
православной стране.
Мне надо переводчик. Русского на английском. Что это слово было? Православно. Православно.
Orthodox.
Понятно.
Среди христиан. Наша культура содержит в себе православие и христианство,
Мгм.
много традиций, идей, представлений. Поэтому, конечно, часть меня, часть моего не характера, может быть, картины мира, да, часть,
Фундамента
да,
личности.
часть
Мгм.
моей картины мира, конечно же, связана с православием, с христианством.
Мгм.
Но я, пожалуй, агностик.
Мгм.
Я точно не атеист,
Мгм.
но мне сложно себя назвать по-настоящему верующим, религиозным человеком какой-то определенной конфессии.
Мгм.
Конечно, православие мне близко и понятно, но если бы нужно было выбирать религию и конфессию, я думаю, я выбрала бы буддизм. Хотя многие
Буддизм.
говорят, что буддизм — это не религия, а философия,
Мгм.
но мне
Это сюрприз для меня послушать. Сколько людей в России буд... буддист? Немного, я думаю.
кажется, буддизм, он где-то на грани между религией и философией. А, Не знаю, нужно ли тут давать свое мнение, почему я так думаю.
Мгм.
А,
Если тебе интересно, если ты хочешь, то да. Если ты думаешь, что это уместно в нашей
м,
беседе, в этом диалоге.
Я постараюсь сказать коротко. А, Мне кажется, любая религия предлагает человеку путь к спасению.
Мгм.
Да, Христос, Спаситель, и так далее.
Куда переводчик? Спасите. Спаситель.
Savior.
М. Так далее.
В буддизме
Так далее. И так далее.
And so on.
Я думал, что это был и так далее. Или что-то. Я понимаю сейчас. Интересно.
также есть идея, что человек страдает так или иначе. Он страдает.
Он страдает.
He is suffering.
И хотя в буддизме нету какого-то бога, спасителя,
Мгм.
а бога нет, но метод, способ спасения себя
Он страдает.
Блин. Способ.
Way.
Да, конечно.
от ужасных страданий есть. Поэтому вот, с одной стороны, Бога в буддизме нет, но путь к спасению есть. Поэтому вроде религия, а вроде и нет.
Мгм. Мгм.
Вроде. Я не... Вроде.
Like.
Хм. Хм.
Понимаю, понимаю. Я
да.
думаю, что еще большое отличие в том, что чтобы практиковать буддизм, недостаточно верить в идею. Я думаю, очень важно, чтобы это было образом жизни. Это
Это было образом жизни.
It was a life form.
Хм.
должен быть стиль твоей жизни. Это не то, как ты думаешь, а то, как ты живешь.
Буддизм очень практичная а, что?
Практичная школа,
Практичная,
практичная философия.
да, такой метод.
Школа.
School.
Он очень инструментальный.
Мгм. Наверное. Я тут я не буду давать комментарии. Мы могли бы
А,
много говорить на эту тему, но я абсолютно не эксперт.
мгм. Ну, пожалуй, это все, что я могу сказать, да, про религиозность.
Мгм.
М, Но
Хорошо.
я за духовную жизнь. То есть я не считаю, что люди — это просто биологическая масса. Есть что-то более тонкое, есть более тонкие материи, которых мы не видим и не всегда ощущаем, но это очень важная часть нашей жизни.
Мгм.
И мне кажется, нужно
Часть на английском это part, да? Часть.
Part.
Отлично.
об этом думать и нужно об этом заботиться.
Мгм. Да,
Блин. Заботиться. Заботиться.
Take care.
Take care.
заботиться хорошее слово. Это правда.
Это был испанский язык. Si quieres ver más videos premium comprensible. Блин.
Правда.
Si quieres ver más videos premium comprensibles en ruso, puedes suscribirte a nuestro perfil en Boosty. If you want to watch more, yeah. kind of forgot I studied Spanish for like 10 years. Or like 10 months. Да, это хороший канал для изучения русского языка. Так, мы вернемся к книге. Книге. Я не знаю. Есть что-то еще? Ай, блядь. So, kind of lost where I was at. P thread, wait, and signal. Yeah, okay. Second case, the child runs immediately. One last note. So to make sure you understand the importance, view alternate implementations. Oh yeah, I was wondering why we needed the state variable done. No, that's real. Imagine the case where the child runs immediately and calls Threxit immediately. In this case, the child will signal, but there's no thread of sweep on the condition. Yeah. I recall thinking that it only worked because the while done just never went into it. It never waited on it. type shit. What could occur here? Third join. Down is equal to 0. Wait. This could go through here, be here, and this executes and it signals. And then it waits and it never catches it. I'm goated. Green. This variable down to 1 signal, but no thread rating on it. Signal threads open. Producer consumer bounded buffer problem. Put and get routines. Producer consumer bounded buffer. Generalized semaphore. As either a lock or a condition variable. Learn more about semaphores later. So get assert count as 1. Put. Let's just read and then go to their one. That's it. One or more producer threads and one or more consumer threads. Dang it, dude. This is why I failed my NVIDIA interview. Because I hadn't read this yet. That's so annoying, dude. Dude, I hate myself. Okay, next. Break me, dude. Actually, just a bot. Damn. Bro. How do I have no ship, bro? I think by this time last year I had a ship. But now I'm like 2x better and I have no ship. Stop complaining and just continue reading. I'm at the very part I messed up on. Instead of reading, I just start complaining. Imagine one or more producer threads and one or more consumer threads. Producers generate data items and place them in a buffer. Consumers grab said items from the buffer and consume them in some way. This arrangement occurs in many real systems. For example, in a multi-threaded web server, a producer puts HTTP requests in a work queue. Consumer takes requests out of the queue and processes them. Bounded buffer is also used when you pipe the output of one program into another. grepfoo file.txt pipe word count-l. Runs two processes concurrently. grep writes lines from file.txt with the string foo, and then to what it thinks is standard output, the Unix shell redirects the output to what is called a Unix pipe, created by the pipe syscall. The other end of this pipe is connected to the standard input of process WC, which simply counts the number of lines in the input stream and prints out the result. Thus, the grep process is the producer, WC is the consumer. Between them is an in-kernel bounded buffer. You are just a user. Bounded buffer is a shared resource and must, of course, require synchronized access to it, lest a race condition arise. To begin to understand this problem better, let's start with some actual code. Okay. First thing we need is a shared buffer into which a producer puts data and out of which a consumer takes data. Let's just use a single integer for simplicity. You can imagine placing a pointer to a data structure into this slot instead. And the two inner routines to put a value into the shared buffer and to get a value out of the buffer. C30.6 for deets. Okay, so here we go. So here's the integer. You have an int buffer. The count is 0. Put something into the buffer. Assert the count 0. So there's nothing in it. Put 1 in it. Buffer the value. Oh, so that means there's something in it. So you can't, so you don't call get on empty. You want to put on a full one. Okay. Get, assert there's something in it, set it to 0 and return what's in it. Okay. Seems easy enough. Pretty simple, no? Yes. The put routine assumes the buffer is empty and checks this with an assertion, then simply puts a value into the shared buffer and marks it full by setting 1. Get routine does the inverse, setting buffer to empty, returning the value. Don't worry, this is a shared buffer, has a single entry. Later we'll generalize it to a queue that can hold multiple entries, which will be even more fun than it sounds. I'm all for it. Now we need to write some routines that know when it is okay to access the buffer to either put data in it or get data out of it. The conditions for this should be obvious. Only put data into the buffer when count is 0 when it's empty, and only get data from the buffer when count is 1 when the buffer was full. If we write the synchronization code such that a producer puts data into a full buffer, we write the synchronization code such that a producer puts data into a full buffer, or a consumer gets data from an empty one, you have something wrong. This work is going to be done by two types of threads. You got producer threads and consumer threads. Figure 37 shows the code for a producer that puts an integer into the shared buffer loops a number of times, and a consumer that gets the data out of the shared buffer. Producer that puts an integer into the shared buffer loops a number of times. Putting it into the same integer in a buffer can loops times. Consumer that gets the data out of the buffer for every time putting out the item from the shared buffer. Producer void arg int I loops int arg, so the arg is just the amount For int I 0 loops put I. Okay. I guess you're assuming there's a buffer size. And consumer while one just constantly spam get. Okay. Now imagine we have just a single producer and a single consumer. Obviously, the put and get routines have critical sections within them as put updates it, get reads it. Putting a lock doesn't work, you need something more. Single condition variable and an if statement. That's something more as condition variables. In this broken first try, we have a single condition variable cond and an associated lock mutex. Let's examine this signaling logic between producers and consumers. When a producer wants to fill the buffer, it waits for it to be empty, P1 to P3. The consumer has the exact same logic, but waits for a different condition, fullness, C1 to C3. So, int loops, con, mutex, mutex. So in the producer, int I. Why is the int I in a different line? Is that a thing? I've never seen that. Maybe that just shows how it slowing up. Okay. For up to loops, lock the mutex. If the count is 1, so we're back to the single case. If the count is 1, wait for the cond. Put I. So we're waiting for the cond. So why is it not while count as well? Thought we just said it needs to be while, bro. Брать, зачем это не while, бля? Put I. Signal call. Huh. So if you have multiple producers, are you just clacked? Are you just murked? Pthread, mutex, unlock, mutex. Consumer void arg, anti, up to loops, mutex, lock. If 0, wait. So I guess the wait signals to the other thing that is time. Okay. Int temp get. Pthread. So we're just printing temp after unlocking and signaling. Ladma. Yeah, I thought the first problem is that the signal, if you have two producers, there's only one signal. Everything's listening to the same signal. So here he's saying the first problem has to do with the if state. Yeah, I was about to say, why is that not a line? Though that might not even, that's probably not even what the problem is, to be honest. Just do the if statement for wait. So there are two consumers, one producer. First, a consumer runs, it acquires the lock, checks if any buffers are ready for consumption. Finding that none are, waits. Dude. I'm raging. Sigh. Input sigh. First, a consumer TC1 runs, it acquires the lock C1, checks if any buffers are ready for consumption C2. Finding that none are, waits C3. Then the producer runs, it acquires P1, checks if the buffers are full P2, and finding that not to be the case, fills the buffer. Then signals that a buffer is filled, moves the first consumer from sleeping to ready queue. Now it's running, then the producer continues to raising the buffer is full, sleeps. Problem occurs, another consumer sneaks in and consumes the 1x value of the buffer. TC1 runs, forgetting to wait, reacquires the lock in the return, they call the get, there are no buffers. Searching triggers, the code is not functional there. Sharp 91. 39 shows the action each thread takes. So yeah, I envision, I saw that. Vision sound like I actually did something. Problem arises for a simple reason. After the producer woke up, before TC1 even ran, the state of the boundary buffer changed thanks to TC2. Signaling a thread only wakes it up. It's just a hint that the state of the board has changed. In this case, the device in place in the buffer doesn't guarantee that when the state will still be as it desired. This interpretation of what a signal means is often referred to as mesa semantics. After the first research that built a condition variable in such a manner, the contrast, referred to as force semantics, is harder to build but provides a stronger guarantee than the open thread will be run immediately upon being woken. Virtually every system ever built employs Mesa semantics. Single CV in a while. Okay, so that's one thing to note. It's still broken. This fix is easy. Change if to a while. Think about why this works. Now consumer TC1 wakes up. Think about why this works. Now consumer TC1 wakes up. And with the lock held, immediately rechecks. The buffer is empty at that point. So if it's while it's waiting, if the condition changes and something else happens, then you still would go to it again. Okay. Thanks to Mesa semantics, a simple rule to remember with condition variables is always use while loops. Sometimes you don't have to, you just do it. There's still a bug. So it's the one where the two consumers both put. Am I tripping? There's only one condition variable? Yeah, because say you have like 30 producers and 30% consumers. This, you could have two producers signaling this. That's and then it signals to this to put again. That's my theory. That's my theory, right? So I don't think I'm right. Problem occurs when two consumers run first, and then both go to sleep. C3. Wait, two producers or two consumers? Problem occurs when two consumers run first, both go to sleep. Then the producer ones puts a value in the buffer and wakes one of the consumers. Producer then loops back. Tries to put more data in the buffer because the buffer is full. Waits on the condition and sleeps. Now one consumer is ready to run. Two threads are sleeping on the condition. We are about to cause a problem. Things are getting exciting. That's a kind of fruity way to go into the next paragraph. Few please. Consumer TC1 wakes by returning from wait. C3 rechecks the condition C2 and finding the buffer full consumes the value. Critically signals the condition on 5, waking only one thread that is sleeping. Which thread should it wake? Because the consumer has emptied the buffer, it should query wake the producer. However, if it wakes the consumer TC2, which is definitely possible depending on how the wake queue is managed, we have a problem. Yes, it's because I believe that is the that's similar to what I said, just from the consumer. But where what was supposed to be a variable of consumers talking to producers is where it's producers talking to producers. So I think I'm solid there. Consumer TC2 will wake up and find the buffer empty and go back to sleep. The producer, which has a value, put in the buffer, less sleeping. The other consumer thread goes back to sleep. All three threads are less sleeping, clear bug. See 3011 for a brutal step-by-step of this entire terrible calamity. Signaling is clearly needed, but must be more directed. Consumers should not wake other consumers, only producers, and vice versa. So imagine they're in here. Two and then the red waiting. You're in here. All that's good. Count 0, put. Condition it. Alright, let's reread this. Two consumers run first. Wake up consumer. Wake up a consumer. Producer then loops back. Tries one more data in the buffer, it's full, waits on the condition. Sleeping. Now, one consumer is ready to run. 2 threads are sleeping. TC2 and TP. TC1 returns from wait. Rechecks 2, find the buffer full, consumes. Okay, so one of them got out. Get. Signals it. But is it this or is it this? Yeah, that's just the inverse of what I was saying. So I'm sure. So the single buffer producer consumer solution. Use 2 condition variables instead of 1 in order to properly signal which type of thread should wake up. In the code, producer threads wait on the condition empty and signals fill. Conversely, so this is just like a FIFO. Conversely, consumer threads wait on fill and signal empty. By doing so, the second problem above is devoid by design. A consumer can never accidentally wake up a consumer, and a producer can never accidentally wake up a producer. Okay, you get the fill and the empty signal. I mean, that just makes more sense from the beginning type shit. So what is this? The correct producer consumer sync? So yeah, this is replacing it with buffer fill pointer. This value. Fill pointer 0, buffer max. So this is like a circular buffer type. I believe that's what they're doing in that. And then the correct producer consumer synchronization. So you have your mutex, you have your lock, and then you're just having the empty, so when count is max. Okay, so this is more bufferish. Yeah, that's chill. Yeah, that's chill. Using a, so use while, not if for conditions. Using while is always correct. Spurious wake-ups and some dark yeah, okay. So what was the most recent thing we said? Fill and empty? I feel like there's like a ton of code and no explanation. Need to enable more concurrency, add more buffer slots. Single producer and consumer is more efficient as it reduces context switches. With multiple producer to consumers, it allows concurrent producing, consuming chase cakes. Fortunately, it is a small change from our current solution. First change for this current solution is to within the buffer structure itself, and the corresponding get put and get. We also slightly changed the conditions that producers and consumers check in order to determine whether to sleep or not. We also show the correct weighting and signaling logic. Producer only sleeps if all buffers are currently filled. Similarly, a consumer only sleeps if all buffers are currently empty unless we saw the producer programs on. I'm gonna sit back and drink a cold one. That's a real shit early. So, okay, this is the code that we're just talking. So yeah, the signal empty, unlock the mutex, and then you have like a ring buffer-ish setup where you have a fill pointer. When does the fill pointer changed? Fill pointer is equal to value. Oh, yeah. Wrap it around. And then use pointer follows. And you just make sure you don't mess it up, I guess. We'll now look at one example of how condition variables can be used. Same group who invented Mesa semantics, Mesa language. 2 is best shown via the simple example. In this case, in a simple multi-threaded memalloc library. Code snippet, you might see in the code when a thread calls in the memory allocation code, it might have to wait in order for more memory to come free. Okay. Conversely, when a thread frees memory, it signals that more memory is free. However, our code above has a problem. Which waiting above? Okay. Our code below has a problem. Which waiting thread? There can be more than one, should be woken up. How many bytes of the heap are free? Bytes to the left is starts at the max heap size. You need a lock in condition, so we have a void pointer allocate. Lock the mutex while there are still bytes left. Size, what is size? Oh, okay, so while there's not enough bytes left, wait. So this wait indicates that there's bytes, that there's more bytes, perhaps. Void pointer. That's a malloc call. Bytes left. Subtract the size. I suppose they're checking that worked. Pthread mutex unlock. Return pointer. 3. Take in the pointer and the size. Lock the mutex. Increase the bytes by the size. Signal. Yeah, you don't know which allocation to signal. Интересно. Is that what it's saying? I mean, I guess that is. So replace pthread signal with pthread broadcast. We guarantee that any threads that should be woken up are. Then you have a negative performance impact. Might needlessly wake up many other waiting threads that shouldn't be awake. They'll wake up, recheck the condition, and go to sleep. It's called a covering condition as it covers all the cases where a thread needs to wake up. Conservatively, they'll cause, as we discussed, is that threads might be overwoken. Astute reader might have noticed we could have used this approach earlier with the single condition variable. However, in that case, we used a better solution. Summary. We have seen the introduction of another important synchronization primitive beyond locks, condition variables. By allowing threads to sleep in some program state is not as desired, CVEs, condition variables, allow us to neatly solve a number of problems, a number of important synchronization problems, including the famous and so important producer-consumer problem, as well as covering conditions. A more dramatic concluding sentence here would be go here, such as who loved Big Brother? Orwell 49. I think that government is double plus good. Right? I mean, the book is free. I'll read your BS. Not BS. I'll read your jokes. I'll read your jokes. Semaphores. Here we go. Do you know what a semaphore is? No. RIP. Okay. As we now know. Now. Let me hit a quick break. Let me hit a quick looking at IP. Let me do a quick analysis that we have 3 chapters left. And I've been streaming for 4 hours. And I'm going to bed in 2 hours. И так далее. So, let's do some quick HTTP requests to keep it general. Normalize generality maximum. Hit a quick browse even. Это мусор. Shout out to homie John Strickland, bro. How do you say semaphore? Semaphore no, it's semaphore. Oh, it's semaphore, okay.
Semaphore.
Semaphore. Okay. So it says we can use semaphores as locks and condition variables. Rather curious. Go-to statements considered harmful. Why is that a great title? Am I stupid? Why is that a great title, bro? Why is the writer of that sentence glazing the out of the title? Bro, why is he writing the title? I thought it was like something actually like clever. Nah, bro's just me writing Dijkstra, bro. So either way, we're going to study the semaphore. Indeed, Dijkstra and Colley invented the semaphore as a single primitive for all things related to synchronization. As you will see, you can use semaphores as both locks and condition variables. Semaphore is an object with an integer value that we can manipulate with two routines. In the POSIX standard, these routines are sem wait and sem post. Historically, sem wait was called P by Dijkstra and sem post called V. These shortened forms come from Dutch words. Interestingly, which Dutch words this supposedly came from has changed over time. P came from passering, to pass. V came from Vrijgave, release. P was from prologue, a contraction of probeer. Try. Попробовать. Интересно. Verlag, Verhoog. Call them down and up. That was a waste of 42 seconds, okay. Sem wait and sem post, because the initial value of the semaphore determines its behavior. Before calling any other routine to interact with it, you must initialize it to some value, as you do in 31. Semaphore.h. SemTS. Seminit SO1. So, okay. So what are 0 and 1? In the figure, we could declare semaphore. Initialize it to the value 1 by passing in 1. Okay, so, excuse me, the second argument to seminit will be 0. And all the examples we'll see, indicating that the semaphore is shared between threads in the same process. See the man page for details on other uses of semaphores, namely how they can be used to synchronize across different processes, which require a different value in the second argument. Okay, so it's like a type version. It's like a comment. After a semaphore is initialized, we can call one of two functions to interact with it, semWait or semPost. The behavior of these two functions is seen in figure 31.2. For now, we are not considered with the implementation of these routines, which clearly require some care. With multiple threads calling into semWait and semPost, there is obvious need for managing these critical sections. We will now focus on how to use these primitives, perhaps later. Later we will discuss how they're built. All right, so what are they? We should discuss a few salient aspects of the interfaces here. First, so what does salient mean? Noticeable, okay. So that word could just be deleted without any loss in anything. What was that? First, we can see that semWait. So we can't really see that yet. First, we can see that semWait will either return right away because the value of the semaphore was 1 or higher. So it's like card counting. That's kind of green. First, we can see that semWait will either return right away because the value of the semaphore was 1 or higher when we call it semWait. So that makes no sense to me. Is it talking about the code? I suppose it's talking about the code. Okay, I think it's talking about the code. Int semWait. So you take a semT, decrement s by 1, wait if it's negative. Hmm. Okay. Wait if it's negative. Definite value specify one. Positive. Wait if it's negative. So you start at however many consumers you have. Started at however many consumers you have. I think sem post increment the value of the semaphore by one if there are one or more threads waiting, wake one. If there is a thread waiting, wake one. The binary semaphore is a lock. Okay, so I've read that. So now jumping. This guy definitely likes his readers, despite not liking go-to statements in general. He definitely likes making his readers go to certain arbitrarily far away figures and then returning. The behavior of these two functions is seen in figure 31 too. We're not considered so salient, thus, so here. First, we can see that sem weight will either return right away because the value of the semaphore was 1 or higher when we called sem weight, or it will cause the caller to suspend execution waiting for a subsequent post. Of course, multiple calling threads may call into sem wait and thus all be queued waiting to be woken. Indeed. Second, we can see that sem post does not wait for some particular condition to hold like sem wait does. Rather, it simply increments the value of a semaphore. And then if there is a thread waiting to be woken, wakes one of them up. Sem post does not wait for some particular condition to hold, like sem wait does. Indeed, it just wakes one up if there is, and otherwise it doesn't do anything. Third, the value of the semaphore when negative is equal to the number of waiting threads. Is that true? What if the semaphore initial value is positive? It's like 10. Oh yeah, well yeah, I'm slow. I'm cooked. Oh, I'm cooked. Okay. Yeah, wait if you're only waiting if it's negative. Okay, I'm collapsed. Only wait if it's negative, so you document first. Binary semaphore, that is a lock. Sem m, I thought we were gonna keep the third parameter at 0 at all times. Huh? So init m started at 0, the third value is no longer 0 originally. And you wait, do a critical section and post. Oh, attention. Okay, binary semaphore is locked. Now you see ready to use one. Using a semaphore as a lock. What should X be? I thought we just said it was always going to be 0. Am I tripping? Ah, the second argument is 0. My bad. He was calling the second argument. He was one indexing it. Noted. So what should X be? 0. It should be 0. Rip, it should be 1. Back. Wait, because you're waiting first. You're going to decrement it. Because I'm cooked. I'm collapsed. I'm collapsed. All right. 5 hours? You're been reading for 5 hours? It's kind of crazy. 313 for a code snippet. Surround the section of interest with a sem wait, sem post pair. Critical to making this work, though, is that the initial value will be 1. Make this clear, let's imagine thread 0, changes to 0, decrement, or wait if it's not greater than or equal to 0, because the 0 symbol was in return. Then you're free to go, and then if there's something else, it'll make it 0, and then wait for the post, and then it'll go. If no, the thread tries to require a lock while thread 0 is inside the critical section, when a lock plus send post. So restore the value of the semaphore to 1 and not waiting thread because there is none. 41.4, such stack trace shows the duration of the scenario. More interesting case arises when thread 0 holds the lock, I use called send wait. When I enter post and another thread tries to enter the critical section by calling send wait. In this case, thread 1 would decrement the value of semaphore to -1. And thus wait, putting itself to sleep and relinquishing the processing. When thread 0 runs again, it'll initially call send post, incrementing the value back to 0, then wake up thread 1, which will be able to require lock for itself, and thread 1 finishes it, making the value semaphore is to 1. Figure 31.5 shows a stack trace this example. In addition to thread actions, the figure shows the scheduler state. Run, ready, and sleep. Thread 1 goes into sleeping state when it tries to acquire the already held lock. Only when thread 0 runs again can thread 1 be woken for an run again. If you want to work through it, you have to try multiple threads queue up. Yeah, so I was kind of envisioning that while I was reading. Thus, we were able to use semaphores as locks because locks only have 2 states. Semaphore used as a lock, a binary semaphore. Note that if you're using a semaphore only in this binary fashion, it could be implemented in a simpler manner than the general semaphores we see here. Semaphores for ordering. Semaphores are also useful to order events in a concurrent program. For example, a thread may wish to wait for a list to become non-empty. So the child posts that it's done. So what happened to the list non-empty thing? A thread may wish to wait for a list to become non-empty so it can delete an element from it. In this pattern of usage, we often find one thread waiting for something to happen and another thread making something that something happen, and then signaling that it has happened, thus waking the other thread. We are thus using the semaphore as an ordering primitive. Simple example is as follows. Imagine a thread creates another thread and wants to wait for it to complete its execution. When this program runs, we'd like to see it fall. Begin child int. So in this case, semin int, what should x be? We'll soon consider that. Begin, create the thread, wait. So it should be 0, because you want it to wait initially. And then this will post and make it 0, and then you're good. Make it 0. 0, yep. 2 cases to consider. First, let's assume the parent creates a job, but the child is not run yet. In this case, parent will call sem wait before the child is called sem post. We'd like the parent to wait for the child to run. The only way this will happen is if the value of the semaphore is -0. Parent runs seconds into -1 while sleeping. Child increments it to 0. Wake the parent. Second case occurs when the child runs to completion before the parent gets a chance to call sem wait. In this chance, the child will call sem post, making it 1, and the parent calls sem wait, making it back to 0, and then just not wait. The producer-consumer balance buffer problem. So this is what my interview was on where I got clapped. The next problem we will confront in this chapter is known as the producer-consumer problem, or sometimes the bounded buffer problem, D72. This problem is described in detail in the previous chapter or condition chapter. See condition variable. See that there. Aside setting the value of semaphore, we're now seeing 2 examples of initializing semaphore. In the first, 1, second, 0. What's the general rule? One simple the way to think about it. Thanks to Perry Kivalovitz, кто это? Это американский. He invented the RAM drive that survives system crashes in 1986. Published the source code to the first keylogger. Get off my lawn. What the frick is this? How a computer geek and his wife survived the zombie apocalypse? What is that? Oh, he's retired? But he's open to work. He lives in Mobile, Alabama. That's kind of dope. Dang, this senior must be crack. Who is it? Nah, dude, shout out whoever that's for, bro. You're goated. Incorrect. No, this is kind of it's kind of Chad right here. You retired and you want to be a hired gun for bugs or software artifacts in C and C++ or ARM. That's kind of dope. Outside expert for code review, constructive criticism. Criticism is crazy. An assessment of code quality for legal or other purposes. Speaker on debugging, code quality, ethics, and responsibility and stuff. He like just retired. HTTP no S, dude. You're trolling me. Bro. You're trolling me, dude. What is this? Forward Pro. Let me close that up. Silhouette effects. Your sciences department. Stony Brook. Then he went to he's just a BS. It appears. Interesting. This has got to be the game dev kid. Nah, I just sniped him, bro. I just sniped that dude. Computer graphics. It's 3 patents. Interesting. Terminal mode. Learning C by reading the source code is directly from Ken Thompson is dope as hell. No, that's crazy. First keylogger is crazy. Or it's just a demon. The dangers of mind control. Academy Award. I thought it was like movies or something. You're gonna die. Consider the number of resources you are willing to give away immediately after initialization. With the lock, it was 1. You're willing to have the lock locked away. With the ordering case, it was 0 because there's nothing to give away at the start. Only when the child thread is done is the resource created, at which point. So, okay. I'm more curious for ones above 0 and 1, where it's like, whatever. Okay. First attempt. So what's the problem again? Okay, bounded buffer. Produce or consume. 2 sems, empty and full, which are threads we use to indicate when a buffer entry has been emptied or full, respectively. So I'm going to skip trying to consider other ones and just continue reading. The code for the put and get routines is in figure 31.9. Our attempt at solving the problem is 31.10. In this example, the producer first waits for a buffer to become empty in order to put data in it. The consumer similarly waits for a buffer to become filled. Before using. Producer waits for a buffer to become empty in order to put data in it. Makes sense. Consumer waits for a buffer to become filled before using it. Let us imagine that max is equal to 1, so we're just having 1. See if it works. Imagine again there are 2 threads, a producer and a consumer. Let us imagine a specific scenario on a single CPU. Assume the consumer gets to run first. Thus, the consumer will hit line C1 in figure 3110. Calling sem wait. Adder full. Was waiting on the full sem. Because full is initialized to the value 0.
break up a pair. Break up a sentence with 40 lines of code. Okay. You love to see it. Because full was initialized to the value 0, the call would decrement full to -1, block the consumer, wait for another thread to call send post on full as desired. That seems to make initial sense. So you have a buffer max, in which case max is just 1, fill and use 0, 0. So these are going to be used to. Isn't this just the old thing? This hasn't changed, I don't believe. Fill, buffer fill value. Wait, fill equals fill plus 1% max. Well, what's 1% 1 is just 0, yeah. It's 0. I think it's 0. Am I cooked? %4 2, 0, yeah, okay. So 1% 1 is 0, so it's gonna stay 0 all the time. And lost you. Producer. You wait for empty. Put, you post as full, consumer waits for full. Grab it, so you can return it after you get out of the semaphore. Then you post as empty. Do whatever you want with it. And main, you init max are empty, 0 or full. Okay. Okay, that makes sense. Thread will decrement full. So this is literally just, this is so easy, dude. Dude, if I just read this like interview, like, if I just read this like a month earlier, I'd just be signed in video right now. And it's like not even hard to understand. It's just like, dude. It's kind of annoying, bro. Somewhere I'm freaking booked. Oh, we'll hit line P1, calling the empty routine. I'm gonna call my grandparents in a while.
Alright. I gotta walk in, dude. I mean, I already have been in the problem. Alright, just keep going. 9 seconds. So, where is it at? This is why you don't split lines of code between two blocks. Let's split sentences between two blocks. For full shots to the value 0. The call would decrement full block consumer and wait for that thread possible. See the producer then runs at a hit line, waiting for empty. Unlike the consumer, it'll continue because empty is initialized to the value max. Thus empty will be decremented to 0. Producer will put a data value in, then the producer will continue to P3 and call sympost full, changing the value of the full sum forward from -1 to 0. In this case, one of two things should happen. If the producer continues to run, it'll loop around at B1 again. That's wash. Producer was interrupted, the consumer ran, will return. Buffer void, translate example. More threads. Still work. Adding mutual exclusion. Incorrectly. Okay. I just now examine that max is greater. Imagine the max is greater than 1. I just assume that there are multiple producers and multiple consumers. I have a problem. Race condition. Can't see it. Where's that? Look more at could and get. I'll see it. Two producers both calling into put at the same time. Oh, they're not even synchronized at all. They were synchronized within waits and posts, or is that only the binary semaphore? So you're saying you're putting a binary semaphore around it? Is that my prediction? No producer PA. gets to run first and just starts to fill the buffer, entry 0. Before PA increments the fill counter, it's interrupted. PB starts to run and I want, so yeah, there's not mutex at all in this kind of adding mutual exclusion. As you can see, what we're trying here is add mutual exclusion. The filling of a buffer and incoming the index into the buffer is a critical section. Filling a buffer and incoming the critical section. The card carefully define binary set of formats. So yeah, add some locks and mutex, 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 and mutex, mutex. Отлично. Doesn't work. Why? Deadlock. It's called a deadlock. Wait, so I was kind of thought this was a good idea, okay. So wait on the mutex, which decreases it. So imagine it starts at, what does this start at? 0, right? No, it starts at 1. Wait on it. You have another producer, wait on it. 2, 0. Yeah, I don't see it. No key, I don't see it. What sequence of steps must happen for the program to deadlock? Imagine 2 threads, 1 producer, 1 consumer. Consumer runs first. Fires a mutex, calls some wait. Oh, that obvious. Consumer runs first, some wait on the mutex. Or we're never even posting to the mutex because we're waiting for it to be. Yeah. Classic deadlock. Solve this problem, we simply must reduce the scope of the lock. Figure 3112 shows the correct solution. As you can see, we simply move the mutex, acquire, and release to just be around the critical section. The full and empty wait and signal code is left outside too. The result is a simple and working bounded buffer, a common use pattern in multi-threaded programs. Understand it now, use it later. You will thank us for years to come, or at least you will thank us when the same question is asked on a final exam or during a job interview. Yeah, I would have. Look, yeah, I would have. That would have been nice to know. But I got thoughts, so I'm ready. Wait, empty. Let's just move the mutex inwards. Oh, the rage is crazy, dude. You're roid raging. But not the roids, just normal raging. I'm coping, okay. I'm phone coping. Let's just get back to reading. Reader writer locks.
Another classic problem stems from the desire for a more flexible locking primitive that adds different data structure accesses. Sorry, that admits that different data structure accesses might require different kinds of locking. For example, imagine a number of concurrent list operations, inserts, lookups. While inserts change the state of a list, lookups just read it. As long as we can guarantee no insert is ongoing, we can allow many lookups to proceed concurrently. Special type of lock we have not developed to support this type of operation is known as a reader-writer lock. Code for such a lock is available in 3113. Boolean. Code is pretty simple. If some thread wants to update the data structure in question, it should call the new pair of synchronization operations. Read write lock, acquire write lock to acquire a write lock, and release write lock to release it. Internally, these simply use the write lock semaphore to ensure that only a single writer can actually acquire the lock. And that's under the critical section. More interesting is the pair of routines to acquire and release the locks, read locks, sorry. To acquire and release, acquire and release read locks. When acquiring a read lock, the reader must first. What am I cooked? What time is it? I'm getting tired or something. When acquiring a read lock, the reader first acquires lock and then increments the reader's variable to track how many readers are currently inside the data structure. The important step taken within acquire read lock occurs when the first reader acquires the lock. In that case, the reader also acquires the write lock by calling sem wait on the write lock semaphore, then releasing lock by calling sem post. Sounds good. Thus, once a reader has acquired a read lock, more readers will be allowed to acquire the read lock too. However, any thread that wishes to acquire the write lock will have to wait until all readers are finished. The last one to exit the critical section, called sim post on write lock, makes it positive, and then you okay, type shit. The approach works as desired, but it does have some negatives, especially when it comes to fairness. If there's a bunch of reads, if there's concurrent or like a continuous time of reads, you just can't write. Better implementation. Think about what you need to do to prevent more readers from entering the lock. The lock will conditional variable that it's waiting, and then if you can just type it. Yeah, I do agree. You should put the mutex in the put and get functions up from like 2 hours ago. Simple. So let's just read this. So you have in your read write lock, you have a binary semaphore for the basic lock, then you have the write lock, and you have the number of readers. So init 0 readers, init both the locks, start at 0. Acquiring the read lock involves waiting for the basic lock, incrementing the, so this is acquiring the read lock, should have said. I think I did say that actually. Acquire the main lock. So wait for writing to release the main lock, then incrementing on readers because you're a reader. If you're the first reader, you also must acquire the write lock. So the binary semaphore is just for the structure in general. So the binary you got to get the structure in general. Then you increment the number of readers. Then you wait for the write lock. Then you acquire the. If you're the first one, you wait for the write lock. Acquire the write lock. Then you post the main lock. So are you actually doing anything? I guess not, because this is just the interface to actually acquire the lock, and you do your stuff before releasing the lock. Releasing the read lock involves waiting for the main lock, then decreasing the amount of readers. If you're the last reader, hand the thing back to the right. Otherwise, just post the main lock back. Acquiring the write lock, just wait for the write lock. Releasing the write lock, just post the write lock. Okay. Reader writer often adds more overhead. They just showcase a use case of simple. Simple and dumb can be better, Hill's Law. Never underestimate the notion that simple and dumb approach can be the best one locking. Sometimes simple spin lock works best because it's easy to implement fast. That's something like reader write sounds cooler than complex equals slow. Mark Hill, dissertation, design caches for CPUs. Simple direct map caches work better than fancy set associative designs because simple designs have faster lookups. Big and dumb is better. type shit. Downing philosophers. One of the most famous concurrency problems posed and solved by Dijkstra is known as the Downing philosopher's problem. The problem is famous because it is fun and somewhat intellectually interesting. However, its practical utility is low. However, its fame forces its inclusion here. Indeed, you might be asked about it on some interview, and you'd really hate your OS professor if you miss that question and don't get the job. Conversely, if you get the job, please feel free to send your OS professor a nice note or some stock options. The basic setup problem is this. Assume there are 5 philosophers sitting around the table. Between each pair of philosophers is a single fork, and thus 5 total. The philosophers each have times where they think, they don't need any forks, and sometimes where they eat. In order to eat, a philosopher needs 2 forks. You need 2 forks. Oh, there was only 1 fork. Oh, between each pair of philosophers is a single fork. Okay. Philosophers each have times where they think and times where they don't need any forks, times where they eat. In order to eat, philosopher needs 2 forks. Contention for these forks and the synchronization problems that ensue makes this a problem. That does sound kind of difficult. Like, here's the basic loop of each philosopher. Assuming each has a unique thread identifier 0 to 5, 4. Think for some time. Get forks, eat, put the forks. Key challenge is to write the routines get forks and put forks such that there's no deadlock. No philosopher starves and never gets to eat, and concurrency is high. Many philosophers can eat at the same time as possible. Following boundary solutions, we'll use a few helper functions to get us towards a solution. They are left return p, right return p plus 1. Okay, so it's like indexed based on the one to your left, and then the right plus 1. Kind of wraps around for 0. Okay. Philosopher P wishes to refer to the fork on the left, call left P. Fork on the right, call right P. Module operator handles case. And like I just said, we'll also need some semaphores. Let's assume we have 5 for each fork. Forks 5. If I attempt our first solution to the problem, assume we initialize each semaphore on the fork's array to a value of 1. Assume that each philosopher knows its own number, P. We can thus write the get forks and put forks routine. So we assume semaphore 1, philosopher knows it's P. We can write put forks and get forks. Broken solution. So the wrong intuition is as follows. To acquire the forks, grab a lock on each one. First on the left, first on the right. So just wait for the left and the right. But you're going to be in a deadlock because you're going to be waiting for one on the left, and the man's going to be waiting on his left, and just waiting on his left, and then you're waiting on the right, but that's also something to the left, so you're just fucked. Phosphor 0 grabs fork 0, phosphor 1 grabs fork 1, phosphor 2, but yeah, that's what I was predicting. And then phosphor 4 can't grab phosphor. Nobody can grab the one on the right, bro. Study deadlock in more detail soon. It's safe to say it's not working. So you got to break the dependency. So, simplest way to attack this problem is to change how forks are acquired by at least one of the philosophers. Indeed, this is how Dijkstra himself solved the problem. Specifically, let's assume that philosopher 4 gets the forks in a different order than the others. But forks code remains the same. Both forks are the same, but if you're the 4th philosopher, you do the right one first. Let me be right. Let's get wrong. So philosopher 4 gets his first. Then he does his eating, and it drops. I think it's fine. Because the last philosopher goes right before left, and just switching with one of philosopher goes 147, and the other side is broken. Yeah, I convinced myself that it works. Other famous problems. Cigarette smoker's problem. Sleeping barber. Dude, what are these problems, bro? No, I'm trying to be a philosopher that's dining while smoking a cigarette and my barber's asleep. Most of them are just excuses to think about concurrency. Some of them have fascinating names. So yeah, thread throttling. It's a form of mission control. That makes sense. Consider a more specific example. Imagine you create 100 threads working on several problem parallel and some problem code. Threads are occupied memory. Even with this, good luck building LLVM. Let's call this part of the code the memory intensive region. So what's it? What are the time? What's the time? Oh, casual 6 of 30. Memory intensive region. If all the other threads are in the memory intensive region at the same time, your sum is bigger than the memory space and the swap space, and your machine will start thrashing. I mean, that's fine. Simple semaphore can solve this problem by initializing the value of the semaphore to the maximum value of the number of threads you wish to enter. Memory post intensive region once, and then putting some weight and some post around the region, the semaphore can naturally throttle the amount of threads that are comparing the data streams in the code. How do you implement them? Low-level synchronization primitives, the lock sync condition variables, to build our own version of semaphores called semaphores. One lock and one condition variable, plus a state variable to track the value of the semaphore. Study the code for yourself to really understand it. One difference is that we don't maintain the invariant that the value of the semaphore numbers affects the number of waiting threads. Value will never be 0. This behavior This behavior is easier to implement and matches the current Linux implementation. Really? So, XAMT, you have a value, a cond, and a lock. Only one thread can call a init, which just inits the cond and inits the mutex and sets the value. It's pretty free. Wait. Lock the mutex. While the value is less than 0. I mean, while the value is less than 0. Wait on the cond. Then decrement the value. And unlock the mutex. And then you're chilling. Post. Lock it. Increase the value. Signal and unlock. Let's chill.
Johnny Lipajabad. What is this person? Underground ass person, dude. Alright, for those semaphores, I would be curious to read a concurrency book like the one mentioned with some exercises and just get cracked at concurrency. Like that's certainly in anyone's best interest. I'm getting quite tired. I want to take a shower. Let me do a calendar check. Hit a scene 2, hit a cal. Thursday, so probably take out my. So I moved dining. I've already dined. I'll probably read some Cougar Natties too. That gives me an hour. Yeah, I can finish the book in an hour. And then laundry tomorrow. Frick. Laundry tomorrow morning. And video OS up 0. So the Zig PR got hijacked. That's fucking annoying. Wasted so much time on that for some random kid. Like, bro. What is you doing, bro? Yeah, that's kind of annoying. Okay.
Dude, I'm tired. All right, stop whining and read. Researchers spend a great deal of time. Oh, common concurrency problems. This. So just wrap it in a mutex. Order violation. Use before initialization. Oh wait, that reminds me. Did I? No, I did not. I've just been reading, looking at myself. Cringe. Here we go. So use condition variables to force ordering. So get a locked and a con initializer. Need the lock to update the con. So create thread. Signal that it's been created. Wait for the thread to be initialized. So that implies having them not lock. While empty it, so wait. And then unlock it.
That is kind of AIDS. So yeah, the easiest way to not write a deadlock is to not have an interdependence on nested mutexes. Ten groups is crazy. Yes. When you have deadlock errors because there are too many locks, simply add more locks. Compare and swap with an address expected and new. Yeah, I guess we didn't really go with this. Address expected. Deref address is equal to expected. Set address to new return 1, otherwise return 0. Atomically increment a value by a certain amount using compare and swap. Do something so atomic increment in value old. Do int old value Wow. I don't fully understand that, but I'm just gonna keep it going. That's chill. Inside the do loop, the new node's next pointer is set to the current head of the list. Okay. Mm. Compare and swap. So if between the two of those it changed, then you gotta redo it. That makes sense. It has changed. Do it again. And it makes it atomic. Okay, let's chill. Yeah, I read about, or I think I audiobooked about MapReduce. All right, this is a short chapter. Let's finish it out strong. 6 hours in. Let's get it. Well, one advance equals get events for event and events process event. Select or pull. While one, initialize the FD set to a 0.
Now set the bits for descriptors the server is interested in. So all of them from min to max. Do the select. Select max plus 1. Check which have data. If they have data processed. What does select do again? Check whether there's any IO. Async IO control ball. File descriptor, file offset. Volatile void, buffer location, pointer, and the length. Okay. So when he was asking me to make the distributed queue system, I was doing like async. Shit, I said with polling. I don't think that was what I was looking for. And I mentioned signals. I don't actually think I did that bad. I just didn't know what a semaphore was. Use signals when async IO completes. State management. Manual stack management. Interrupt seg v. So yeah, I don't know. I didn't really get way too much from that, but first, just write a simple server. Okay, dang. Let's read this BS at the end. Taking two Motrin tab? What is Motrin? Pain relief? Okay. Yeah, that is true. It is kind of crazy. Like 5 lines of code is freaking impossible to understand. Kind of mess with that. All right. Wow. So, um, wow. Okay. So yeah, wow. That was Dude. Oh my god, bro. Just sitting here for 6.5 hours just reading about concurrency. What did I do this morning?